Okay, so this is our 10th lecture, and we finally will begin talking about the subject of the lectures. Okay, so I'm just going to dive right in because we're pretty much ready to go at this point with definitions. Okay, so again with our philosophy, we're going to be talking about things with general degrees of regularity. Of course, for many applications of control theory, holomorphic control systems are not maybe so interesting. However, they do provide us with some interesting mathematical examples that we can contrast things with. So that's worth talking about. Okay, so the usual regularity indices, and then a C nu. Double pair. Okay, so it's an M and an F. Okay, and we'll typically use a symbol like that, which is so that you can reproduce it in your own writing. Okay. So M is simply manifold, the space of states for your control system, and F is a presheaf of sets of C nu vector fields. Okay, so that means, remember, that to every open set U, you assign a subset of C nu vector fields on the open set U, and you have to have the restriction property that if V is contained in U, then when you restrict a vector field on U for your system F, it becomes an element of the system on the open set V. Okay.
So no algebraic structure on these sets?
None whatsoever. Yeah. You really have to have no structure because remember, well, we'll see the examples, and I will try to remember to address that point there. Yeah. Okay. So that's not a word that I want to, or a collection of words I want to write very often, so I'll just abbreviate it like that. Okay, so we'll say it's complete if F is a sheaf. Okay. And we'll say it's globally generated if there exists some subset, which I'll write script X, of global vector fields defined on M. And again, there's no algebraic structure for these, just a subset of vector fields. So I think I had defined this notion of globally generated when we talked about sheaves and presheaves. Okay. Okay. So that the vector fields of your system on the open set U are just restrictions of these global vector fields from the set script X. Okay. All right, so the first thing we should do talk about examples. Okay, so the first thing is that if you have a control system in the sense that we talked about before, I forget the order I used. Maybe I used that. Okay, so a control system in our previous language, remember, consisted of a manifold, M, a topological space, C, which was your control set, and then a mapping, F. So I'll remind you how that goes, because there's one important facet of that definition of our definition of a control system that's going to be important for us here. So remember that F maps C cross, I think I actually typically do this. Okay. And so for a fixed element of the little u, let's say, of the control set, so that means fixing this argument, then you're going to have a vector field, because of course this is going to map x to the tangent space at x. And we require that this mapping from C, okay, into the space of C new vector fields is continuous. Okay, this is sometimes equivalent to some standard assumption that people make in control theory, but sometimes it's not a standard assumption that people make in control theory, but it's the one that we want. This is the property of, this is the definition of control system that will be useful for us. Okay? So this is what we had called a C-nu control system before. Okay, so the standard class of control systems is often C1 control systems, or Rob is often talking about C-lib control systems, and then he has some extra condition about uniform boundedness with respect to U. Okay.
So, can you remind me? So M is the manifold.
Yeah.
What is the C?
C is an arbitrary topological space, which is where your controls live. So the control values, not the controls as functions of time, right? So these are not control functions of time. These are just, for like a linear system, this would be Rm. Yeah, so a simple thing. But in this general framework, it's an arbitrary topological space. Okay.
But isn't it only specified by F itself? No, I see. Okay.
Okay.
It takes U as the input.
Yeah. Okay. So F sub U is if I take a control value U and freeze it, that gets me my dynamics. So that's like a constant control. Okay. It's important to understand that. Okay. All right. So corresponding to a control system like this, we have a tautological control system. Okay, and I'll write that as G sigma. Okay, so this is going to, M is of course going to be the same, and I'll have some presheaf F sub sigma of vector fields, and it has kind of the obvious definition. Okay, so the presheaf here will be of the globally generated variety. Okay, and so the vector fields on an open set U are simply going to be the restrictions of these guys. Okay, so it's going to be Fu restricted to capital U, where U is in C. Okay, so this is of course a globally generated tautological control system.
Notation, just for
Sure, yeah.
For the presheaf, maybe make the U more capital.
Oh, so yeah. Okay. we're not going to be doing a lot of normal control theory, so this hopefully won't come up too often. Okay, so that tells me a way of going from a normal control system to a tautological control system. What about going backwards? Okay, so can I start with a tautological control system and reacquire a control system? Well, the answer is no, generally. But you can, in a relatively obvious way, if your tautological control system starts out being globally generated. Okay, so if we go from a control system to a tautological control system, we end up with something that's globally generated. To go back, you have to start with something that's globally generated. Okay, so if G is a globally generated tautological control system. Okay, so here notice that you end up, if you have a globally generated tautological control system defined by a family X of vector fields, then X is equal to the sections of the presheaf over M. That's just obviously true. Okay, so frequently when I have a globally generated tautological control system, I'll just write the set of global vector fields that define it as F of M. Okay, no extra notation for those. Okay.
In the definition for global generation,
yeah.
You specify how U is measurably depending on...
No, so U here is an open set in M. So it's an open set in your set of states, so there's no ambiguity there, right? So it's just an open subset of a manifold, okay? And so these are vector fields, okay, defined on the open set U.
How do you go from that definition to the control definition? How do you construct your U? How do you construct your...
So remember, the U's here in the presheaf are arbitrary open sets, okay? So I think you're running into the confusion of big U and little u. So let me maybe give this definition, and I think it probably answers your question. Yeah. Okay. So I'm going to start now with one of these that's globally generated. I'm going to define a control system. I think that's what you're asking me. Okay. So if I start with one of these, we define a C-new control system. Okay. So I'm going to write this as sigma G, okay, this is going to be an M, okay, then I need a control set and an F, okay, so my control set is going to be, I'm going to write it like that, because the control set is only going to depend on F, of course, and then I'm going to have a capital F, like that, okay, so how's this defined? Okay, so my control set is simply the set of vector fields, global vector fields that define the tautological control system. Okay. Then what is F, capital F? Okay. All right. So it's going to be a map from M cross F of M. Okay. So now it's confusing, right? So you have to make a choice. So an element of this control set now is going to be a vector field, okay, a globally defined vector field on M. Are you going to write a vector field as little u, or are you going to write a control as capital X? Okay, either way requires squinting to understand, and I'm going to make the choice of writing an element of the control set as capital X. Okay, but this now, in this world of thinking about things, that's a control. Okay. All right. So the rule is that this should define for me an element of the tangent bundle, and it should be at the tangent space at X. And then there's only one way to assemble this notation to give me a thing in the space that I want, and that's that. Okay. All right. So you can see now. Okay, so this there's one thing you have to check here. Okay? You have to check that this thing is a C-new control system in the definition that I give. Okay? And that's where this definition of C-new control system that I gave here, okay, which requires that this map be continuous, okay, that's where that is part of the check. Okay? Right? Because now you have to check. So what this means is you have to check, and now it's really just a tautology, that x maps to x, okay, right? This now is a point in the control set, okay, and here it's an element of the space of C-new vector fields. Okay, you have to check that that map is continuous. Well, the identity map is continuous. This is one of the reasons why we call these tautological control systems.
And how crucial is this continuity condition?
It's required here. So in other words, if you're going to recover a control system from a tautological control system, this map has to be continuous.
If you replace that with measurability, for example.
So there's no measurability here, right? So measurability comes in when you're talking about time, right? And we haven't talked about time yet. Okay. So this so way it works with time is that if you prescribe u as a function of t, okay, then you need measurability of the map that goes from t to u of t to here. And then if this map is continuous, then that map will be measurable.
I would like a question, a general question about this.
Yeah.
Field, basically. Is this condition basically standard?
Yes, I mean that's an excellent question. Normally if you look at papers on nonlinear control theory, right? You have a map like this, okay? Then you give some conditions on this map, right? So a typical set of conditions is going to be that it should be jointly continuous, all right? Just as a map from M cross C into Tm, which is a very different thing from continuity of this map, okay? And then you'll normally require some conditions on either a Lipschitz constant or a derivative, okay? So you'll require that that there should maybe be a Lipschitz constant, so that independent of u, okay, so uniform in control, that makes this mapping from now x into Tm Lipschitz, or differentiable, or twice differentiable. So those kinds of conditions are standard, and that would correspond, in my case, to choosing nu to be lip, or 1 plus lip, or 1 or 2, right? So we recover those kinds of conditions. This stops being standard for nu equals infinity, okay? That's not standard. It's well known in some areas, okay? Some people understand that that's the right definition to use in the smooth case, but many times what you see is you see things like this. You see, for fixed u, this mapping should be smooth, okay? And then you put conditions, like I said, about Lipschitzness. That's really not a natural condition, because you're mixing regularities in some sense. And you have more smoothness for fixed u than actually you're able to use with your other hypotheses. By requiring this map to be continuous, everything sort of coheres. Yeah. And in the analytic category, this definition is new. It's never been used before. Yeah.
So one question. So you go from classical control system, let's say, to tautological, and then here you should have to go from tautological to classical. But that operation is not a right inverse to this one. So
no.
You start from classical and you go to tautological.
Oh, so I will talk about all of these questions.
Yeah.
I will give the results.
Because that construction doesn't give you.
I will give the results.
Okay.
Yeah. Of course, I considered that question. Okay, but first I want to give you a ton of examples of these things. Okay. All right. So so I'm going to use script x for something different here. It won't be a family of vector fields here. X is going to be a differential inclusion. Okay. So what this means So what it means is that x evaluated at a point x is going to be a subset of the tangent space at x. Okay, that's what a differential inclusion is. And then normally you put some regularity assumptions on that, and I'll talk about that. So I think you had asked me a question at the very, very first lecture about differential inclusions, and then I said I would answer it, and then I didn't. So I'll address all that stuff now. And I'll be able to do it much more comprehensively now than I would have then. So I will say what I would have said then, plus much more. Okay? Okay. So we associate a tautological control system, which I'll write as Gx. Okay, so the manifold will be the manifold, and then what I'm going to do is I'm going to define a presheaf, okay, of vector fields associated with this differential inclusion, and it kind of has the obvious definition. Okay. All right. Okay, so first of all, a little piece of notation. Okay. So I'll kind of do this just notationally in stages. So the first thing I'm going to do is I'm going to define this object. Okay. So it's going to be they're going to be a set of C nu vector fields on U, and they're going to have, of course, certain properties, and you can guess what it's going to be. So it's going to be vector fields on U with the property that when you evaluate them at every point in U, you end up with something in there. Okay, so for an arbitrary differential inclusion, that set will typically be empty. Okay. All right, so this has to do with recovering things from, going back and forth between certain kinds of constructions. So we're going to have all kinds of versions of that question that you asked, going back and forth from systems to differential inclusions and so on. So, but I want to get all the mappings for which we will try to construct inverses first. Okay. So then I need to define this, and now it's going to simply be okay. So this notation I think is just a little bit clearer than this notation, but that's what this set of vector fields on U is. It's just those vector fields on U, C nu vector fields on U, which take values in the differential inclusion at every point in U. Sorry, this should be for every x in U. Okay. All right, so now the mapping, of course, from a differential inclusion to a tautological control system will frequently just have no value whatsoever. Okay, so as I say, and so you can start putting assumptions on x, like semi-continuity assumptions. Still, generally speaking, the set will be empty. Okay, differential inclusions are way too flexible to be able to say anything about regularity. Which, depending on your point of view, is an advantage or a disadvantage. All right, and so you can also go from so let me just say here, so the presheaf Fx is a sheaf. Okay, you can just prove that just by using the definition of sheaf. Okay, so this is a way, okay, and one of the things that we're going to see in example 5 in this list is that this presheaf generally does not arise like that, so it's not generally globally generated. Okay. All right. Okay. So So now we're going to go from tautological control system to differential inclusion. That construction is also quite obvious. Okay, in fact, this construction, and we're also going to go from control system to differential inclusion. That's kind of a well-known thing. But what we'll see is that this construction is actually a more natural construction than the construction going from control system to differential inclusion. So we're going to define a differential inclusion. Okay, so it's going to be XF. Okay, and this is easy. Okay, so I need to give you a subset of the tangent space at X. And this is simply going to be, you take tangent vectors at X, which are evaluations of vector fields, which are in the stock of the presheaf. Sure, yeah.
I think this part is probably one of the most important discussions of the whole theory.
Yeah, I agree. Yep.
I think we should.
You should understand it, absolutely, yeah.
So, basically for inclusion is a set value mapping. So then basically we can't just define point-wise characterization. We have to put a.
You have to put some way they join together, yeah.
How do you basically when you say differential inclusion, do you like?
So the way I've said it, there's no regularity of the different, like these, and that's why this set will generally be empty, right? If you just put no assumptions whatsoever on a differential inclusion, this will be empty, right? There'll be no way of finding, say, a C1 vector field or even a continuous vector field that lies in the differential inclusion at every point, right? That will generally not be possible. So, then you need to put some assumptions on a differential inclusion. All right, the normal assumptions that people put on differential inclusions are semi-continuity assumptions. The differential inclusion is lower semi-continuous, and I'm not going to define what all that means, okay? So there's some regularity kind of assumptions that you can put on differential inclusions. And then the existence of things in here, right? So when these things are non-empty, okay, these become selection theorems. Okay? Yeah. So normally selection theorems are continuous selection theorems. Right? But I'm talking about things that are very regular, okay? So even if you have continuous selections, okay, you may not have differentiable selections or smooth selections, and analytic selections will generally not exist at all because analytic things are just too rigid, okay? So even if you add some normal regularity assumptions to your differential inclusion, like semi-continuity, these things will still be empty.
So what about the case where your manifold, you're looking at sub-Riemannian?
Yep. Manifold? Okay, we'll talk about that. We'll talk exactly that. I'm going to have a ton of examples here. That's going to be one.
And that fits in this differential inclusion framework?
Let's when we get to how I'm going to talk about sub-Riemannian things, let's ask that question then. Okay. Yeah. Okay. All right. So this is a way to go from. So this is all great. I'm glad you all are having these questions. It means you're right along with me. But we'll talk about it. And some of the questions I'll be able to answer. Some of them I won't be. I can promise you that. Okay. So this is a very simple way to go from a differential inclusion to a tautological control system. Okay. Oh, sorry, the other way around. I apologize. From a tautological control system to a differential inclusion. So now Reza will ask, when can you go back and forth between these? The answer, of course, is almost never. Yeah. But we'll get to that. All right, so now we have three objects that we're talking about, right? We have tautological control systems, we have control systems, and we have differential inclusions. We go back and forth between these. The only thing we're missing now is going from control systems to differential inclusions, and maybe back, but that's not something we're going to talk much about. Okay, so let's just talk about this. Okay, so the construction here again is it's classical. Okay. All right, so this is a well-known thing that people talk about. And then again, so now you can ask, if you have a differential inclusion, can you construct a control system associated with it? Well, you can. It may be completely worthless. Here's how you can do it. You can somehow, associated with a differential inclusion, okay, I can maybe define a set of globally defined vector fields which have this property, right? So I could take gamma nu x of m. Okay, I could take that as my control set and then do that construction over there. But generally, it's a meaningless construction. There's just too many things that. But you can still do it. It just doesn't necessarily give you anything useful. In kind of the same way that going from a differential inclusion to a tautological control system generally doesn't give you anything meaningful. Okay. All right. So we're going to continue with something. So these are. So what after I give my list of examples. Okay. Then what I will do is sort of write down what correspondences there are between these things. Okay? And really the most important correspondence for us is going to be the correspondence between a tautological control system and control systems. So we're going to talk a lot about that. And then what I will eventually try to tell you is that you should stop thinking that that's important and you should just start thinking about tautological control systems and kind of forgetting about control systems. Okay? Yeah. No.
But so the tautological control system is defined by a pair. You have the manifold and you have that presheaf.
Yeah.
Whereas the standard control system is a triple. So you have the manifold, state space, control set, and you have the law, basically. Dynamics in some sense. So why call the tautological control system tautological control system? Why not just a presheaf of vector fields?
I mean, it is, but it's going to have a ton of extra structure that you wouldn't. There's, when we start talking about trajectories, for example, right, which we have no idea how to do for a tautological control system at this point, right? Then the control system part of it is going to come in. So by all means, right? But there's some control theory we're going to do with presheaves of vector fields. So, and the fact is that there's, also, and I think that if you just think about presheaves of vector fields, and that's what you think about in your head, you're not thinking about control theory. And so, for example, it's not obvious how you're going to construct a control system from a presheaf of vector fields, right? Or even that that's an interesting thing to think about. So the language just suggests that there should be. So I agree, it's just language, okay? But we're going to, we're going to end up with a control theory here, right? So this is the analog of our, so, when I have a control system as a triple, right? An M, a C, and an F, there's no trajectories there, but that's my system, right? That's the basic data that defines the system. For a tautological control system, for which we're going to have trajectories and all the stuff that you can do with control theory, that's what the system part of that definition is. So it's analogous to control system for tautological control theory, right? It's the basic data that you start with. It's just, your question could as well be phrased, why don't I just say manifold topological space and mapping F satisfying these properties? Well, it's a lot of words in that case, but the question that you ask really is that. It's just that happens in the tautological control system case that, the C and the F get sort of bundled into this thing which has a nice description, presheaf of sets. But really the questions are the same, and you should think of them as being the same, and so then, it's just language. Yeah, absolutely, yeah. I think that once we start going down this road, the question washes away, so it's the usual thing in mathematics, right? You don't understand something, but you become familiar with it. Okay. So you'll become familiar with it. Okay, other examples. Okay. All right, so what we're going to do now is we're going to consider a situation where we have dynamics which are defined on open sets. Okay, so in other words, on each we have an open cover of our manifold, and on each of these open sets, U sub A, we're going to have some dynamics that we can prescribe. Okay. So we're going to go with F sub A, is going to be a subset of vector fields on U sub A. All right, so now what I'm going to do is associated with this data. Okay, so is it clear what I have? So on each of these open sets, I have a family of vector fields F sub A, and that kind of defines my possible dynamics there. Okay. So associated with this data, I'm going to define a tautological control system. So obviously I need to define my presheaf of sets. So I take an open subset U of M, and I need to give you a set of vector fields here. Here's the definition. So it's going to be let me see about how's the best way to say this. So it's going to be so what it's going to be is I'm going to take vector fields from each of these guys for the UAs, which sit inside U. Okay, so what's the best way to say that? So it's going to be X restricted to U, okay, where X is in FA, okay, so it's a vector field on right, okay. So this is more, this is more complicated. So what I need to be able to do, so the UAs have to sit inside U. So it's going to be vector fields. Let me see if I'm going to write it down and see if I can catch up as I go along. Okay. So that X restricted to UA. Okay. So so UA here is going to have to sit inside U. Okay. So this set could possibly be empty, you'll see, and that's not going to cause any problems for us. Okay. So that X is restricted to UA is an element of FA, and this has to be true for every A, for all A's, such that UA is contained in U. Okay, so it could possibly, I could patch one together over UAs that overlap, and both are contained in capital U. Okay, so it's kind of a complicated definition. As I say, for a large U, okay, it's possible that F of U will be empty, okay, and there's no problem about that. Okay, this definition is, presheaves can assign empty sets to open sets. Okay, and one of the things that we're going to see is the way that you patch that up is by not considering presheaves. You really want to consider sheaves, and so what you're going to do with this, what you're really interested in here, is the sheafification of that, and we'll talk about that. Okay, but it covers this case. So, for example, this is the framework that Sussman uses to study his very general version of the orbit theorem. Okay. All right. And the point of that example is to show that the tautological control system framework covers a lot of things that people talk about.
I'm sorry, I think it's the framework that Stefan used for his orbit.
Also Sussman, yes.
Something?
I mean, open covers, right? So Sussman talks about vector fields that are partially defined. Yeah, that's what we're talking about here. So let me do sub-Riemannian geometry. Okay. Okay, so I'm going to first define clearly what I mean by a C new distribution. Okay. Sorry. I need one more piece of data here. So there's a neighborhood UX of X and C new vector fields, which I'll write as little x sub x. And these are vector fields on U sub x. Okay, such that. Okay, so then that's d sub x. So this is the fiber of the distribution over the point x, which is d intersects with the tangent space at x. This is equal to oh, and this should actually be y. X. Oh, sorry. This should be this. Okay, y. Okay, next. Okay, and this should be true for every y in U sub x. Okay, so the point is that I can find some C new vector fields defined in some neighborhood of every point, so that my distribution is just the span of those vector fields at that point. Okay, so the existence of this neighborhood and of this family of vector fields is how you specify the regularity of the distribution. Okay. All right. Now, corresponding to this, we associate a tautological control system, and so that'll be okay, so I need, of course, to tell you what the presheaf f sub d is. So it's vector fields of class C new on U such that x sub x is in d sub x for every x in U. Okay? So this is very much similar to our differential inclusion construction. Okay? And really here, of course, we have a differential inclusion, and the differential inclusion is just this subspace d sub x at every point. Okay? All right, so you had a question about subrahmanian geometry. Now is the time to ask it. Does this?
Yeah, I think that answers it.
Yeah,
It's
okay.
it's a nice example of differential inclusion that has some good
Regularity properties, exactly, yeah. Okay. All right, so okay, so you can easily check this is a sheaf. Okay. So the interesting thing here, an interesting question to ask, is this globally generated? The answer is no, generally. Okay, it'll be globally generated, you know, if D is one-dimensional or something like that. Okay, and even then, you need some topological conditions for the existence of a continuous non-vanishing vector field. All right. So generally speaking, this will not be a presheaf. This will not be globally generated. However, FD is not generally, but there is an interesting related statement. And actually what I'm going to do is I'll save this related statement for later. Okay, because I want to talk systematically about this process called sheafification before I do that, because what we'll see is that in lots of cases, FD may not be globally generated, but it is the sheafification of a globally generated sheaf. Okay, all right, so I think that's all I had in the way of examples. So there's lots of questions here that we can address. Okay? Yeah.
Suppose I have a map from N to the field space.
Yeah.
And
from the manifold into
vector fields. The control free.
So do you mean into here or into here?
Into TM.
Yeah. Okay. Yeah.
And ask one question. Find the smallest class of controls for which you can represent this as a control system.
Well, I mean, in this case, this is just a vector field, right? If you just have a map from here into here, it's just a single vector field, right? So, you know, as a control system,
then it's upper one. Maybe I'm just.
Yeah.
Maybe I want to go from the let's say the inclusion set, for example.
Oh yeah.
To a control characterization.
Yeah.
And I want to ask the question.
Yeah. That is an interesting question. I think the answer is virtually untouchable. Right? I think there's really nothing there because you know, the differential inclusion framework is just too flexible, and the process of going from differential inclusion to control system, you just have to put some. And I will give you an example of structure on a differential inclusion, which makes the answer to that question nice. But what you see then is that it sort of makes differential inclusions boring.
But you should be able to say, for example, let's say that you give the homeomorphism characterization between different, say, Polish spaces.
Yeah.
So you know that we cannot use a finite set or a countable set.
So for example, okay, if you think about going from differential inclusions to, say, continuous selections, right? So these are already now really hard theorems. You know, lower semi-continuous differential inclusions have continuous selections. Okay, so that's a hard theorem. But from the point of view of tautological control theory, it's a useless theorem because it's a single selection, right? So it just says, that says that at every tangent space, you can find a single tangent vector in your differential inclusion, and you can patch those together in a continuous way. That doesn't mean that you can find for every tangent vector at that point a continuous selection that equals that, right? So those are called parameterization theorems, right? And those are virtually, as far as I can see, non-existent. There's very, very few parameterization theorems. There are some continuous selection theorems, but parameterization theorems are hard to come by. And those are the ones that give you the nice correspondence between differential inclusion and a control system. Yeah, the selection theorems they don't tell you very much, really. It's like also about trajectories, right? If you have a differential inclusion, it has trajectories. Well, that just tells you that trajectories exist. From a control theoretic point of view, that's not very useful, right? Because you want families of trajectories going in all possible directions prescribed by your control system. But so if you just have the existence of a single trajectory, that's kind of boring. And it tells you that your differential inclusion may be kind of too big, right? There'll be parts of your differential inclusion that you don't use to describe the dynamics of your control system, possibly. I am of the opinion that for lots of questions in control theory, and certainly geometric control theory, differential inclusions are just not useful. Yeah.
Can you explain why it's not globally generated?
Yeah. Actually, let me save that. But yes, I will answer that question, but maybe not right now.
Okay. Can I ask then, globally generated? Do you need a single vector field?
It means exactly that FD on every open set is the restriction to that open set of some globally defined vector field. That's what it means. Okay. So let me tell you just a simple reason why this can't be globally generated. Okay. Because if you take, let's say you take D to be TM. Okay. And you take U to be some, let's say let's make this concrete. Okay. And let's take U to be the open ball with radius 1 at the origin. Okay. Now take a vector field on U which blows up at the boundary of the open ball. That's definitely going to be a section of this guy over the open set U, but it definitely will not be the restriction of something globally defined. Okay. So that's one. There's many ways that this isn't globally generated. This is the most boring way.
No, that's interesting.
Yeah, yeah. Okay. All right, so I'll give you sort of a more interesting way in which this thing isn't globally generated. There's many reasons that it's not. You know. Okay. So what time is it, by the way, just so I know? I can budget.
55.
55. Okay. All right. Okay. So let's at this point, before we get to talking about correspondences between all of these things, let's talk about sheafification. Okay. So completion of tautological control systems. Okay. So really I'm talking about sheafification in the general setting here. I'm just going to give the definition in this specific case. So corresponding to every presheaf, there's a canonical way of defining its sheafification in arbitrary categories. That I suppose the category probably has to have some, I think the condition for sheafification to exist in an arbitrary category is that the category should admit equalizers. So that's often true.
Sorry, what is an equalizer?
The existence of some arrows in some diagram. It's like a pullback, right? Pullbacks is about existence of arrows, and equalizer is about arrows in some certain kind of diagram that looks like this. Yeah, so whatever, right? Yeah, they exist here. Okay. All right, so how do we define this guy? Okay, so the sheafification of F is a sheaf, therefore it's a presheaf, so I can tell you I should tell you what its sections are over an open set U, and the sections are like this. They're of course vector fields on U. Okay, and what's the condition? The condition is that when you take the germ of this vector field at a point X in U, that it should be in the stock of the presheaf. And this should hold for every X in U. Okay, that's the sheafification. All right, so when I talked about presheaves and sheaves, I gave you an example of a presheaf that wasn't a sheaf. Okay, so I will just talk in words through that example. I don't think I need to write it down. Okay, so let's consider the presheaf of bounded vector fields. Okay, so we have a Riemannian metric, and we can use that Riemannian metric to say what it means for a vector field, of course, to be bounded. So that means on every open set U, this presheaf is going to be the set of all bounded vector fields on that open set U. That presheaf, as I told you, is not generally a sheaf. And the reason is that boundedness, if boundedness holds locally, it does not have to hold globally. Okay? So if we take that presheaf of bounded vector fields, okay, I claim that its sheafification is simply the set of all vector fields. All right, so let's see that that works.
Sorry,
Yeah.
Isn't that condition always satisfied at the germ?
No, it's not, and I'm in the process of giving you an example where it's not. Yeah. So, all right, so you're with me with the example, or were you off thinking about something? Okay, all right, so we have the presheaf of bounded vector fields, okay? So I'm going to claim that its sheafification is the set of all vector fields, okay? So, so first of all, okay, the set of all vector fields is certainly contained in the sheafification. Let me first think about that, okay? And why is that? And that's because if I think about this condition, okay, what is this condition? This condition says that the vector field X at point, the germ of the vector field X at a point X should have a bounded representative. Which vector fields have bounded germ representatives? Every vector field, right? That's a null condition. It just means in some neighborhood it's bounded. Every vector field has that property. Okay. So this is kind of this is a vacuous condition on the set of all on the set of sections. Okay. So this tells you that the sheafification must contain, or sorry, the sheafification must contain the set of all vector fields. Okay. And then the sheafification is, is the smallest sheaf which contains F. So this proves that the sheafification is the set of all vector fields. Okay. So you should think about that. Why it is that this condition is not always true. Okay. Because remember, this is remember we're defining this, not and this is just one part of the condition. Yeah. Okay, so we're defining vector fields on the open set U.
But you're starting with X, which is already a section of T.
Yeah, but not bounded though, right? So this condition can hold whether the vector field X is bounded or not. In fact, this condition will hold for every vector field on U, right? Because every vector field is equivalent to a bounded germ.
Because I'm thinking of X restricted to U as being already a representative of that equivalence class, but it may not be so.
It need not be so. Yeah, that's right. Yeah. Sorry. That's maybe the point that's confusing here. When I'm taking this germ representative, I mean the germ representative in the sheaf of all vector fields. Yeah. That's maybe the confusing point here. Okay. So this means the germ in the sheaf of vector fields. Yeah, not in the sheaf, of course, because then that's vacuous. Yeah.
So maybe it'll get a little more sticky in like analytic case or something.
That's right. So, well, no. Even in the smooth case, this sheaf of the only time that the sheaf of pre-sheaf of bounded vector fields is going to be a sheaf is when the manifold is compact. In fact, no, I take it back. It's never going to be a sheaf because you can take non-compact open subsets and it'll still fail there. Yeah. So,
I'll ask you a question.
Yeah.
Related to what I guess
Yeah.
touched on. It seems to be a very generous result. Basically, the condition is a set of all vector fields.
Well, in this case, it is. In the case of the sheaf of bounded vector fields, it just happens to be. So let me give out. So when we talk about other examples of pre-sheaves that are not sheaves, you'll see other ways in which the sheaf condition can fail. So maybe it'll clarify that.
What this is telling us is that suppose you have two U's, two sets of U's, and they're essentially equivalent in the sense that when you try to have a condition, they have the same.
So I think this becomes clearer with more examples. But it is something important to understand, so I don't want to leave it without understanding it. But maybe other examples will clarify. Okay. So what I will do now is I'll sort of look at some of the examples that we have, and so for example, I told you that this sheaf is not globally generated. So one of the interesting things here is are globally generated pre-sheaves sheaves, and the answer is almost never. Okay, so all right. So another thing that we'll see is that generally speaking, sheafification is not an easy thing to understand. Okay, in this example, it is. Okay, which is why it's a good example, but it's also why it's not a good example, because the sheafification is easy to understand, it's not capturing a lot of reasons why the sheaf condition fails for a pre-sheaf. So we'll see other interesting examples of that. Okay, so I will not give a specific example because you don't really need a specific example to do this. Okay. All right. So it's something that you understand best by looking at pictures. Okay. All right. So first, let me just sort of draw the setup here. So I'm going to take two disjoint open sets. Okay. Now, what I really need here is I need for there to be let's think about it this way. Suppose I have my presheaf, okay, is going to be defined. So what are my global, right, so this is globally generated, right? So it's going to be defined by globally defined vector fields. So I need to tell you what these vector fields are. And they're going to be constructed in kind of a slightly funny way here, but nevertheless this illustrates one of the reasons why these globally generated sheaves are not, globally generated presheaves are not sheaves. Okay, so it's going to consist of two kinds of vector fields. So it's going to be some class, and I just need some sets of vector fields with x such that the support of x is in U1. Okay, so it's going to be not, I don't mean the set of all vector fields, but it's going to be some family of vector fields that are non-zero on U1, okay, or on some subset of U1, but are 0 on U2. Okay, and then I'm going to have some other vector fields, x, whose support is contained in U2. All right, so so I claim that this presheaf, okay, so this is now a family of globally defined vector fields, so I have the presheaf associated with that. I claim that that presheaf is not a sheaf. Or, yeah. All right, so let's see how this works. So what do I need to do in order for this not to be a presheaf? Well, it should fail the gluing condition. Okay, it turns out that presheaves of sets of vector fields always satisfy the other sheaf condition, which is the separation condition. All right, so it's the gluing condition that's going to fail. And so I'm going to take U is U1 intersect U2. Okay, and so remember what the gluing condition is. It says I take an open set U and I cover it with some open sets, and here I'm going to cover it with U1 and U2. And if I have sections on each of these U1s and U2s that agree on their overlap, then there should be a global section of U. Okay. All right, so let x1 be in F of U1 and x2 be in F of U2. Okay. Then x1 and x2 agree on the intersection. That's one of the conditions. That's the condition for the gluing condition. Okay, because the intersection is empty. There's a condition that they agree is vacuous. Okay, but there exists no x in F of U such that x restricted to U1 is in F of U1. Okay, and so I need a condition here. These should be non-zero. Okay, so both x1 and x2 should be non-zero vector fields. Okay, so then this will be true. And x restricted to U2 is in F of U2. Does that make sense?
Why is that? Why can't?
Because if there's 0, then this could possibly be true.
Oh, no, but why doesn't there exist an x?
Right, okay, good, right? So suppose you have a vector field in F of U with, right, so suppose you have a vector field in F of U, okay, period, okay? So that means it has to be in this set or in this set. because that's what f of, right? So it has to be a restriction to u of something from here and something from here. As soon as it's in here, its restriction to u2 will be 0. So it can't agree with x2.
I think the support is including U1, I see.
Yeah, okay, and yeah, okay. No, I wrote this wrong. I said the right thing, but I wrote it wrong. That's what the condition is. Okay. That's why I need for x1 and x2 to be non-zero. Okay? So this is one of the ways in which a presheaf can fail to be a sheaf. Okay, so now let's look at a special case of this. Okay? All right, so let okay. Suppose now that we want to try to recover the control system from the differential inclusion, okay? As a system, all right? So what would that mean? So what I need to do is I need to, one way to think about that is that what I need to do is I need to recover this collection of vector fields. Okay? So I generally will not be able to do that. In the naive way, I should say. Of globally defined vector fields. Okay, so let's call it f x sigma. Okay. So what's the set of vector fields going to be? It's going to be just the set of set of global vector fields, which take values in the differential inclusion at every point. Is it clear what I mean here? Okay. If you were going to construct a control system from its differential inclusion, this is how you would do it. Okay, you define this family of vector fields, and then take f of x. Okay, so really this is a tautological control system kind of a construction now. Okay, because your control set, okay, is going to be this. So as we're going to see, there's no good correspondence here. Okay, so I'm not saying that this recovers the control system, and so one of the points here is I'm going to explain why. Okay, so a capital F is going to take a vector field from here, and of course it's going to give me. What's certainly true is that this is in here. Yes. X sigma of x. Okay. So it's a reasonable construction. Okay. Now we know that this presheaf is globally generated. So therefore, this presheaf is never going to be a sheaf, or seldom a sheaf, or corresponding kind of arguments that I gave over there. Okay, and moreover, will relate poorly to sigma, to, I should say, this set of vector fields. Okay, and the reason that this will relate poorly to this set of vector fields is kind of given by that. This guy is going to contain many more vector fields, possibly, than this guy. All right. So, going from a differential inclusion to a control system is generally not very good, and it kind of has some relationships to sheafification. Okay. So another question you can ask. Okay. So given a tautological control system, okay, we can associate a differential inclusion that we talked about before.
Andrew, how do we construct F here?
Oh, this F?
Yes.
Right, I mean, just by this, right? So remember my control set now when I'm going backwards, so actually finding the control set C just from a differential inclusion is impossible, right? Because that mapping which goes from control set to vector field may not have actually nice sort of invertibility properties, right? So this set is going to be too big generally. And for the reason is kind of the example that I gave here. So the this set will not understand that you had two separate controls defining this one and this one. Yeah, so it can't distinguish those things.
So then, to understand,
Yeah.
For every x you define a map.
Yeah.
And then you assume there's some measurable selection hypothesis somewhere, which you didn't discuss.
Not measurable, right? I mean, we need much more than measurable. Yeah.
That we don't discuss.
Yeah, no, that's right. I mean, those questions are, are just they're difficult, and my feeling is they're irrelevant for the kinds of things I want to do here. For the reasons I said, there's even if you have continuous selections, there's not necessarily enough of them, right? Yeah. So.
But basically, because one of the reasons for this lecture series is control theory without controls, right?
Yeah. And so that's right. So the point is the differential inclusions are also a way of doing control theory without controls. Yes, exactly. And the point is that my way of doing things in tautological framework and the differential inclusion way of doing things are really very different. Yeah, but they both kind of accomplish something. The problem from I'm not saying that differential inclusions are wrong or stupid, right? But from my point of view, where I'm interested in geometric constructions, so geometric means generally, when you talk about geometric control theory, you're talking about smooth at least, right? Differential inclusions are ill-suited to talking about smooth things. Yeah. Okay. And then, so for a tautological control system, we can associate a differential inclusion, and then you can associate a family of vector fields. Okay. And the question is, when is that true? All right. So again, this can fail in a number of ways. Okay. So note that. So one of the things that I told you was that if you start with an arbitrary differential inclusion and then you define this presheaf of vector fields F corresponding to that differential inclusion, that's always a sheaf. Even when F is not. Okay, So therefore this association of a differential inclusion to a presheaf, and then from the associated differential inclusion back to a sheaf, that will generally not end up back where you started. And that's one reason why. There are other reasons why too. Okay, so here's another reason why. Okay, so what we'll do is we'll take F to B. All right, so first of all, we're going to take M, because now we're going to work with a concrete example. Okay. We're going to take F of M. Okay, so we're going to define a global generator for this sheaf, presheaf, sorry, and this is going to be this vector field. Okay. All right.
So the fact that it's always a sheaf, as opposed to sometimes
A presheaf, yeah. Yeah, exactly, yeah.
What impact does it have down the road, let's say?
It is really not conclusive, right? So we're interested in this question, right? When does this hold? Well, there's a number of reasons why it can't hold. This is one reason why. Okay, but it's not the only reason why, unfortunately. Okay, here's another reason. So there's a number of things here. Yeah, it's not, like I said, it's not. It doesn't lead to some major conclusion, unfortunately. Well, nothing true can be unfortunate, I guess. In math, at least. Okay. Okay, then what is this? Okay, so what's the differential inclusion associated with this tautological control system? Well, so you just take the, so I should say, this is the span. So I'm going to take the subspace span by that, just to keep things simple. Okay. Okay, so obviously when x is non-zero, it's going to be everything, and then when x is 0, it's just 0. Okay, that's the differential inclusion. Okay, so now consider the vector field y, which is just x d by dx. This is a global section of this differential inclusion, smooth, analytic even, right? Okay, but y is not in here. Okay, yeah, no, I'm almost finished. Okay, all right. So we see that sheaves and sheafification can get you some of the reasons why you get a failure like this, but not everything. Okay? So sheaves can help you understand why certain things aren't true, but they don't give you conclusive answers to a lot of things. Okay, so what I will do next time is I will talk about the first question that Abdulreza asked about so this we're not really touching here upon anything to do with equivalence of control systems with tautological control systems, and that's somehow kind of the most important one, right? Excuse me, so next time what I'll do is I'll start talking about when those two things are kind of the same, and when you can go back and forth between them without losing any information.